Now, the next topic under Unit 5 I'm going to discuss is reformulation. See, some formula, what we discussed in the previous sections, we are going to little bit change the format of. That is called reformulation. We are going to study, under reformulation, we are going to study already defined definitions. The defined one, that is the definitions, we are going to view it in a different way. That is called reformulation topic. There is nothing new in this topic. We are going to simply analyze the already discussed definitions in a different view. But we keep in mind that slowly we are moving from set of all real numbers to metric spaces, a general space where the distance is given by the metric rho. So that we have to keep in mind. So we are going to generalize all the formulae, whatever definitions we studied recently, maybe in the 4th unit. So now, so first, in the definition of continuity, continuous function at the point A. So we say that if suppose I say that a function is continuous at a point at the point A, then I can write this one. Whenever x comes very close to A, f of x comes very close to f of A. This is true. And as per the definition, for given epsilon, there exists a delta greater than 0 such that so usually we write like this: 0 x minus a is less than delta implies f of x minus f of a is less than epsilon. That is, usually the definition of continuity we studied is strictly greater than 0. That is, what's the meaning of this is, set of all points whose center is A and this is A plus delta and this is A minus delta. So if you expand this one, so all points inside this interval except at the point A. If suppose A is also considered, then we can remove this part. So this definition holds even if x is not only close to A but equal to A. See, there is a difference between a real number x that is close to A. That is, it comes very close but it won't be equal to A. And both the directions. If it is a one dimension, one real line. If it's a 2 dimension, we come in many directions. Okay. So this definition holds even if this x happens to be A. So this one we are going to remove in future. So hereafter we will write simply that whenever x is coming very close to A, this x can be equal to A also, then f of x comes very close to f of A. So this is the first reformulated. Already we formulated this one. Again we are just redefining. This one is we remove it. So hereafter continuity means without writing this strictly greater than thing, you can simply write only this part. Okay, so this first one you can keep in mind. Just a minute, it got stuck. Okay. Okay. So now the next thing is the very important thing, set of all open balls. So the very important definition which will be used throughout this real analysis subject. The definition, very important definition. That's the definition. First we will go for real line, then I will generalize for metric spaces. What is an open ball? So first I will explain what is an open ball in a real line, R1, not R square, R1. Then I can generalize it for a general metric space. So first an open ball in R. What is an open ball in R? We are going to first I will state the definition, then we will discuss what is the geometrical meaning of open ball in real line, in R square, in R cube. But up power 4 we can't visualize it. Up to 3 dimensions I can visualize what is an open ball. So all other higher dimensional spaces we can't visualize it. Now then finally I will generalize it for a metric space. So now if suppose I take a point in A in R and a real number R greater than 0, we define an open ball that is called as, we use the symbol B of A semicolon R. This is a set. Open ball is a set. So I am going to define what is this. Open ball is the set of all real numbers x in R whose distance to A is less than R. This is the definition of this set B of A semicolon R. That I will write it as a set notation. What is B of A colon R? It is a set. We give the name it as open ball and we name this A as the center and this R is called as the radius. Since it is a ball, we say that its center, some center is there and radius is there. So what is the meaning of this set is set of all real numbers x in R such that the distance between x and A is always less than the radius. This is the meaning of the set B of A colon R. That is, for example, this is the real line, this minus infinity to plus infinity, this is a set of all real numbers R, and suppose this is a A. What is this B of A colon R? A semicolon R is, center is this, so this is nothing but the set of all elements whose distance from A is less than R. So suppose this point is A plus R, this is A minus R. So actually if we expand this, what I get? Set of all elements x minus A less than R and minus R, add A throughout, so what happens? A minus R less than x less than set of all elements that lying between A minus R and A plus R. Suppose this is one general element. Definitely this element whose distance is less than, the distance between x and A is less than R. So all the elements which satisfies this property will be inside this open ball. This set is called as B of A colon R. Okay, so this is called as B of A semicolon R. That is, we call it as open ball centered at A with radius R. This is the center of this center and this we call it as radius of this open ball. Okay. And why we call open ball is all the elements should be strictly that distance between that element x and A, the center must be always less than what? The radius. So these two endpoints are not included. So we put a hole here. All the points inside this will be there. Even A also will be inside this open ball. Okay. So this is the meaning of open ball. This is a new definition and very important definition. And this open ball on real line, we can write like this also, A minus R to A plus R, an open interval, I can write like this. Now we are going to define a continuous function on real line in terms of open balls. That is the next thing. That is why this topic we call it as reformulation. Already we studied some definitions. Now we studied a new concept called open ball. So now we are going to redefine all the studied definitions in terms of open balls. That's why we are not going to change any meaning of that. Simply we are going to use the new the concept, that is basic open ball, and we are going to redefine what is a continuous function on real line. So what is the function f is? Suppose f is continuous at a point A. So what is the definition says? Limit x approaches A, f of x equals to f of A. That is, whenever I already removed this one, x minus A, whenever x is very close to A, f of x is close to what? F of A. Okay, so this is what. Now we are going to write it these things in terms of open balls. So how can I write this one in terms of open ball is, see, this set is nothing but this is a center and this is a radius. And here for this function both domain and codomain are real numbers, because I am not going out of real numbers now. And f is a function from this one, and this is x coming very close to A. X is a general element of R, this domain, and f of x is mapped to f of x, A is mapped to f of A, and f of x comes very close to f of A. So so now as we just defined the open ball, so what is the meaning of this set is, this A is the center and x is delta is the radius and x is the general element. Here for this one, this is the center and this is the radius. So how can we redefine using the open ball concept? So this can be written as, so x is an element of the open ball A colon delta. So this is not, so if I say that, so what is this open ball B of A colon delta? That is nothing but, suppose A is a center, this is A plus delta and A minus delta. So if I write like this, what is the meaning? Our x is inside this set. So if x, this one, we are writing like this, that's all in terms of open ball. So x minus A less than delta, we can write it as x belongs to the open ball A colon delta. If x belongs to this interval, that is, if x is element of this open ball, the meaning is x is very close to A, then how can I write this in terms of open ball? So the center is f of A and radius is epsilon, and this is an open ball. So when x is an element of this open ball, my f of x must belong to this open ball. And very important is, this open ball is in domain, is in the domain of f, and this open ball is in the codomain or range. The codomain or range of the function f. So that's all. Hereafter we can define a continuous function of real line to real line in terms of open ball. So I just explained you. Already we studied the definition. Simply we are changing the view. In terms of open ball we are defining. That's all. We are not going to study any new concept. So this chapter is fully reformulation. So now here we are going to, another one definition we are going to say in terms of continuity, that in terms of inverse functions we are going to define the continuity of a function. So now another thing, suppose a simple example I am going to give. So if you understand this one, I think you can understand the next definition I am going to explain. So now suppose a general function, as maybe the real valued function. Suppose there are three elements are there. Suppose A, B, C, and many elements are there. Suppose there are many elements. Only these three elements are mapped to the same element. say h. So the meaning is f of a is equal to h, f of b is also equal to h, f of c is also equals to h. So now, and suppose it is an one-to-one function, so inverse function exists. So what you can tell about f inverse of h? F inverse of h is not a single element, it contains three elements. What are they? The inverse image of h is a, b and c. And clearly this is a subset of, suppose this is the domain is a and codomain is subset of a. So this concept you have to keep in mind. So whenever we take inverse image, it may be a single element or it may be a set that is a subset of the domain. Okay, this thing you have to keep in mind. So now I am going to define the same continuous definition in terms of inverse functions. That is, we write like a theorem. See, the real valued function f is, the real valued function f is continuous at the point a in R if and only if. Always definitions are if and only if statements. If and only if the inverse image under f of any open ball b of f of a called about f of a contains an open ball a about a. That is, in words this is given, and now I am going to return in terms of inverse images. It is, for any given epsilon greater than 0, there exists a delta greater than 0 such that the inverse image of b f of a colon s should contain the open ball b of a colon delta. See, what is this is? For example, everything we cannot visualize it. Since it is a real line, we can just imagine some geometrical views. So now, see, this is x. Suppose f is a function from this domain to codomain. You think like this is a and this is b, and both are real lines. Suppose, both are real lines, and this is x. X comes very close to a. So this is f of x comes very close to f of a. So now, what is the usual definition of using the open ball says, whenever our x belongs to this open ball whose center is a and radius is delta, then our f of x belongs to the open ball whose center is what? F of a with radius epsilon. This is the usual definition of continuous function at the point A in terms of open balls. Now, in terms of inverse functions, what it says is, so the same, this is for given epsilon, there exists a delta greater than 0 such that, so this is the definition of continuous function in terms of open balls. So same thing in terms of inverse functions, what we are going to do is same thing. For given epsilon greater than 0, there exists a delta greater than 0 such that the inverse image of the open ball. See, for example, I will just little bit erase these things and I will draw the open balls alone now. Suppose this is an open ball. Think that this is open ball, whose center is what? A, and radius is R. I say that X is belonging to this open ball. X is somewhere here. So what is the meaning? The distance between X and A is less than R. That's why it is inside this open ball. If this X is inside this open ball, I name this open ball as B, center radius is R. If this is happens, then there is another open ball here whose center is f of A, whose radius is epsilon. So what is the definition says is my f of x is somewhere here. So when x is belonging to this open ball, my f of x belong to the open ball in the range, that is whose center is f of A colon epsilon. So now I am going to define in terms of inverse images, that is see, think of this. This inverse image is not a set. Okay, it's not a single element. It is a set. That one you have to keep in mind. For that one, I simply given this graph or the diagram. So whenever you take inverse image, it is not a single element. Not always. It is a set. Always. Very rarely it becomes a single element. So now in terms of inverse images, so now what is the inverse image of this open ball in the range? F of A colon semicolon. This inverse image contains this inverse image. If you take the inverse image of this, definitely it will be somewhere here. Okay, so if you take the inverse image of this open ball, it will come here. It will be here, and this, that is also a set. That set should contain this open ball. So that's what. If you take the inverse image, okay, take the inverse image. See, this is the inverse image. The inverse image, if you take, that will come over here. That contains this open ball. Okay. This contains the open ball. Which open ball? A, center A, and radius. Sorry, not radius is not R. Sorry, I have to change it. As per the definition, it should be what? Delta. Okay, delta. Okay, so this is the latest definition of a continuous function at the point A, in a general point A. So now, if I say that I took a general element of a set and I showed that the function is continuous at a point A, then I can say that the function is continuous at every point of A. So that's why we take a general element, an arbitrary element. So if I say that a function is continuous at a general point of a set, then simply I can say that f is continuous. That meaning is f is continuous at every point of that domain. Okay. So that's also next we are going to discuss. In this chapter fully we are going to study the definitions which is reformulated one. Already we studied, and in terms of open balls we are studying. And now finally we studied sequences. The same thing I am going to define in terms of open balls. Limit of a sequence in terms of open balls. limit of a sequence in terms of open balls. This is the next concept we are going to study. So in general, what we studied, we say that a sequence approaches a limit L or a limit A, suppose A. If I say that a section approaches A, for only if for given epsilon greater than 0, there is a capital integer n in I, sorry, not capital, capital N, that is a positive integer n in I, such that whenever n is greater than or equal to this capital N, my sequence elements will come very close to A. That's the meaning of this. So now, how can we define using an open ball in real line, for example? So, same thing, n is greater than or equal to capital N implies, how can I write these terms of open ball? This Sn must belongs to the open ball A colon epsilon. So, how is it geometrically I can view is, this is S1 and my limit is somewhere here, and you think that this is my suppose this is our capital N, S1, S2, sequence elements, slowly it is coming towards what? A. S4. They are very far away from A, but after this N, for this epsilon, I find one N, such that after this N, so what happens? There exists an open ball. Sorry, we should not write open ball like this. Sorry, in real line, open ball is an what? An open interval. This is an open interval. What is this open interval? It is nothing but A minus epsilon to A plus epsilon. This is A minus epsilon, this is A plus epsilon, and it's an open interval. After this N, what happens is, all the sequence element is inside this open ball. That is the meaning of this. Okay? So this is how we understand sequences and relate with open ball. The limit of a sequence relate with open ball. Okay? So